Yesterday we saw that the BRST anomalies arose from zero modes of the kinetic operator, which is like some charge of the measure.
The ghost number anomaly, actually.
Ghost number anomaly, okay. That is unrelated to, or can you clarify the relationship between the ghost number anomaly and gauge anomaly? I think I might have asked that before, but.
So when people say anomaly, there are two different possible meanings to the word, in the sense that global symmetries can have anomalies, and it's fine. So the anomaly of a global symmetry is just a statement that this global symmetry sometimes fail in a controlled way. On the other hand, the gauge anomaly is a more serious problem because it means that your gauge theory is inconsistent. So an anomaly for a gauge symmetry is a very serious problem because if the gauge symmetry breaks down, then the gauge theory just doesn't work. It means that configurations of fields which were supposed to be equivalent are not actually equivalent. When you have in BRST quantization, gauge anomalies tend to manifest themselves into BRST anomalies, meaning that the whole BRST setup still makes sense, because after all, the gauge symmetries have been fixed. But you will not be able to do the Q-close modulo Q-exact step to extract the physical theory. So typically, if you start with a theory which has gauge anomaly, and you BRST quantize it, you will end up with a Q-square that does not vanish. For example, in string theory, if you start from a setup which has a wild anomaly, because the central charge was not zero, then Q-square will be proportional to the central charge.
Is there a set of locus in which the Q does vanish, Q-square does vanish, even in those cases?
I don't think so. I think Q-square is proportional to an operator.
Okay.
Now, the ghost numbers anomaly, so it's not a problem because we're not gauging the ghost number symmetry. It's just a fact, even a feature. It tells you that in order for a correlation function to be non-zero, you might have to put certain more B's than C's or more C's than B's in your operators. Then it connects this with the difference between the number of gauge degrees of freedom and the number of gauge fixing conditions that you imposed. So in general, it's hard and not even desirable to have as many gauge fixing conditions as gauge freedoms. You really only care about having a situation where the difference between the two is finite dimensional, so it's still manageable. And then the ghost number anomaly helps you keep track of this fact. For example, soon we'll be able to do calculations like this. We'll have some surface which has some asymptotic ends. Yeah, when I draw this, I don't mean a boundary, okay? I really mean a cylindrical end that goes to infinity. Where we put some BRST cohomology as in and out states. Of course, as in quantum field theory, what you call outgoing and incoming legs is a bit arbitrary in the sense you can do analytic continuation to move legs in the Feynman diagrams from the past to the future. So I could have just put all outgoing, all incoming states, would have made no difference. But anyway. Now, if you remember, these ground states had Gauss number -1/2, right? So here you might be worried that I'm trying to, well, okay, here you're not going to, right, so you might worry that the total Gauss number of the states I've inserted in here might not be 0. Okay, here it probably works, but if I just put an extra leg going down, right, you might really worry that I started with something that had Gauss number 3/2 and end up with something that has Gauss number 1. So you can ask, how did this happen, right? And the point is that there is a Gauss number anomaly on an interesting surface like that, which makes up for that and makes it work. So anyway, our strategy to compute something like this will be to do a Wild transformation, which is outside of our standard gauge symmetries. What do I mean? As I mentioned, when you think about the gauge symmetry of this surface, you really think about Wild transformations or diffeomorphisms which leave the asymptotic ends not changed. Right? So the gauge symmetries here are typical things which leave the asymptotic ends into semi-infinite cylinders. But the quantum field theory is invariant under pretty somewhat more general Wild transformations, actually. So you can find Wild transformations which shrink, which sort of bring in and compactify these semi-infinite cylinders. A bit like the stalks of a snail, nice stalks of a snail. So there are Wild transformations which map this surface into a sphere with a certain number of special points, one for each puncture, one for each tube. So that somehow time evolution along these tubes become radial evolution towards this point. So when you do this slightly more general Wild transformation, you need to understand how to deal with boundary conditions. So here we're imposing boundary conditions by putting states, because the boundaries, the asymptotic boundary was a circle. But here, this whole asymptotic boundary has been mapped to a point. So I cannot put states anymore here. Instead, all I can do at the point is to put local operators. And today I will describe something called the state operator map, which I believe you've already encountered in conformal field theory, which tells you how to map a state into an operator in such a way that the two answers are the same. So that the quantum field theory calculation here, two-dimensional quantum field theory calculation here, gives exactly the same answer as the two-dimensional quantum field theory calculation here. Or if you really don't like working with a sphere, you can also leave some, say, two asymptotic ends and transform the others in operators. So there are so using the state operator map, you can play around with your surface to a bigger degree than before. So you can add or remove these asymptotic semi-infinite cylinders at the price of inserting appropriate operators. And this is something you can compute. Right? Actually, once you know what the operators are, we already knew how to work on the cylinder. We could just do calculations on the cylinder. Or we can learn how to work on the sphere, which is actually somewhat simpler, and never think about states anymore. Just local operators on a sphere. Any questions? Okay, so as a preparation to this, I think it's just fun to look at some simple Weyl transformations. For example, let me start from the plane with your standard metric, the z bar. Okay, the actual metric is the z bar over 2i, but let me ignore 2i. Just like that. So let me do a Weyl transformation where I map the metric to the z bar over z squared. Okay. Actually, sorry, let me start with another thing. Let me start with 1 plus z squared squared. Can anybody guess how does the plane look like when I put this metric on it?
Sphere.
That's right. So this metric has a nice property that if you change coordinate from z, that it treats, okay, see, that if you change coordinate as z goes to 1 over z prime, the metric remains unchanged. You can easily check it. So this metric treats infinity in the plane in a way that is very similar to the origin. Near the origin, it doesn't do much because this vanishes, right? So the origin remains a normal point, and so infinity must become a normal smooth point. And yes, when you check in detail, you discover that this is just the round metric on the sphere. In stereographic coordinates. Remember, stereographic coordinates are the ones that you obtain when you sort of map you put your plane here, and you map points starting from the South Pole. So you map this point here, you map this point here, you map this point here. And the South Pole is mapped to infinity. So, I mean, I cannot write a global coordinate on the sphere because it's not a plane. But I can take two patches, one patch that covers the sphere except the South Pole, and a patch that covers the sphere except for the North Pole. And then the natural coordinates in those patches are z and z prime. So to be precise, I'm not just describing to you the sphere, I'm describing the sphere as a complex manifold, because I'm giving you complex coordinates on the sphere. The sphere as a complex manifold is also called a complex projective plane. So I'm describing the sphere with two patches, coordinates z and z prime, and this is the round metric on the sphere. And actually, it turns out that in conformal field theory, it's kind of more natural to think about the sphere than the plane. When you say I want to do correlation functions on the plane in a conformal field theory, you need to be quite careful about the boundary conditions at infinity and how to describe those. But on the sphere, you don't need to worry about boundary conditions, because everything is compact. You just put your local operators on the sphere. Anyway, so this is a nice Wild transformation. So let's say this is z equal to 0, and this is z equal to infinity. So the plane is equivalent to the sphere minus 1 point. Now, another not interesting wild transformation maps the point minus the origin into an interesting place. So let me write a metric on the plane minus the origin. Can you guess what this surface looks like? Sort of blowing up the neighborhood of the origin, right? On the other hand, is shrinking infinity, but not as much as we're shrinking infinity here, right? Here, the metric behaves like the z bar over z to the 4th. That's what makes infinity into something smooth. So this is sort of not enough to make infinity smooth, and it's blowing up the origin a bit. Well, try the coordinate redefinition z equal to e to the s. So this becomes ds bar. What does this do? It takes the plane minus the origin and maps concentric circles around the plane into circles of finite of constant length 2 pi. Essentially what it does is transforms the plane into a cylinder. The concentric circles around the origin become just the circles that make up the cylinder. And the radial lines become the time evolution in the cylinder. Okay. So in particular, the plane minus 1 point is equivalent to a cylinder. So z equal to infinity has been mapped to the future past, to the far future, and z equal to 0 has been mapped to the far past. And of course, incidentally, this also tells you that you can map the cylinder to the sphere, where the north pole of the sphere goes to the far future, and the south pole of the sphere goes to the far past. So if you want the sphere, it looks like it's like a cylinder with endowed with a non-flat metric. So let's do the coordinate transformation. We get something like, let's see if I can remember it. It looks like this roughly, if I remember correctly. Sorry. Anyway. Okay. Now that we learned which kind of singularities of the metric we need to have infinite tubes, semi-infinite tubes, we can have more fun. For example, what if I take a metric on the plane that looks like the z bar times 1 plus 1 over z minus z1 squared plus 1 over z minus z2 squared plus 1 over z minus z3 squared. Can you guess how this surface is going to look like? I probably wanted to square the whole thing. Sorry. Did I? No, this is fine. Okay. Can you guess how this surface looks like? How does the metric behave at infinity?
Like a cylinder?
No, it goes like 1, it's still flat.
Okay, that helps.
So at infinity, it's still flat. Not much has changed. What happened near Z1?
Spikes at all those points?
Not quite spikes. Because the z bar over absolute value of z squared is not a spike. It's a tube. So this looks like a plane with some tubes merged into it, where the infinite far of the tubes correspond to the points Z1, Z2, Z3. Now, if I were to remove the 1, then indeed infinity will start looking like a cylinder too. And I will get something that looks like this. But actually, infinity doesn't even have to be a special point. If I were to look at a metric that looks like the z bar, and then some linear combination of things of this sort, with whatever numbers you want to put here, well, this surface will look like this, where z equal to infinity is now a perfectly smooth point, because this metric behaves like 1 over z to the 4th. And here I was talking about z and z bar as they were coordinates on the plane, but they could have as well been coordinates on the sphere. Right? So these sort of wild transformations give you ways to transform the sphere. Gives you that, ways to map the sphere into a funny surface, and vice versa. Any questions? No? Okay. I hope it's no questions because this is clear, and not no questions because I don't know what's going on. Or something in between. Please ask questions now because I want to move on to the state operator map.
So what's the take-home message from this?
The take-home message is that instead of doing calculations on that funny surface, we can do calculations on the sphere, as long as we understand how to map the boundary conditions at asymptotic regions to boundary conditions in the neighborhood of a point.
Using, for example, this last,
Yes,
the second to last.
for example. That's right. So this wild transformation is precisely what I need to map a 3-point scattering amplitude to a sphere, 3-point function.
So if you can file transform any tree level diagram into a sphere, where do the moduli spaces of the different tree level diagrams go?
Well, so I said I can map them to a sphere with some special points. So it turns out that those moduli are hidden in the location of the points. Actually, that's an important point. I should discuss it before I discuss the state operator map. So in a moment. Also, I was a bit hasty when I said that we can do everything in the sphere. We can do everything that is tree level using a sphere. If you wanted something more complicated, like a loop diagram, which has handles, then there is no way to map it to a sphere. Instead, the best you can do is to map it to a torus. You can still retract the 4 stalks into points, but you have to do calculations still on a torus with 4 special points.
So you're doing Weyl transformations in the 2 surface, but is that gonna affect the x mu's?
Well, because the theory of the x mu's is Weyl invariant, so for sure, if I had left the asymptotic ends untouched, for sure the answer would have remained the same. Now, because I'm retracting these asymptotic ends into points, in order to get the same answer, I need to understand what to do at those points. So there is this X gradient, which is the state operator map. It maps a state to a local operator in such a way that the left-hand side equals the right-hand side.
And could you still do this if you hadn't big rotate in the world sheet? All these transformations?
Yes. Now, in principle, you could even try to use complexified Weyl transformations to change the signature of your metric and complexified coordinate transformations. Now, as I said, it's easier to work with Euclidean metrics. And then sort of complexify. So instead of sort of weak rotating the matrix, it's easier to first go from matrix to complex structures and then learn how to weak rotate the complex structures. For example, as I'll explain in a moment, the complex structure of the surface on the left is encoded in the positions of these special points. And so thinking about weak rotating the matrix on the left-hand side turns out to be essentially the same as complexifying these points, which means writing expressions where z and z bar are not conjugate with each other. I will come back to it. Anyway, so this pattern continues. It turns out that the only topological invariant of surfaces like this is something called the genus, which is the number of handles. It can be measured by integrating the curvature of the surface. So if I were doing just standard Weyl transformations with nice boundary conditions at infinity, then it turns out that the integral of the Ricci curvature will be constant. Essentially because it's a topological invariant of the surface. When I sort of shrink these tubes into points, I change this integral by a very precise amount. So for example, here, the cylinder has no curvature anywhere. When I shrink the 2 ends of the cylinder, I end up with a sphere, so the integral of the curvature on the sphere is, I believe, 4 pi. I don't remember it correctly. Anyway, once you normalize it properly, you get 2. Whereas there's a contribution, there's sort of every tube you squeeze with cuisine shifts the integral by 1 unit. So for example, here, if you were doing the integral of the curvature, you get minus 1. And then when you shrink 3 tubes, you land again on a sphere, which is 2. If you're doing the integral of the curvature on this surface, you will get something like minus 4. And after you shrink the 4 legs, you go to 0, which is the total curvature of the torus. In general, the most general diagrams you get will be a surface which has a certain G handles and a certain number of punctures. And the space of complex structures will be the space of complex structures of surfaces of genus G with n punctures. Okay. So now let's try to discuss these moduli spaces a bit for genus 0. So for the 3-level case. Because we'll never do loop calculations in the course. So suppose I have this sphere with n marked points. And I fixed a lot of my gauge freedom by saying that the metric is the z bar. If I fixed all my gauge freedom, are there any diffeomorphisms that can map the sphere to itself and leave the metric unchanged? That's right. Rotations definitely do the trick. But actually, the gauge freedom is bigger than that, right? What we really do is when we set up the problems, not as much as that we set the metric, but rather we say we give a complex structure, right? We pick a complex coordinate. So a better question from me would have been, are there maps? Are there any global coordinate transformations? Can I find another sphere with points in a different location and a different coordinate, z prime, and a map between the two? That's right. It turns out that you can set z to be a z prime plus b over c z prime plus d. So this map blows up only at one point, and it sends it to infinity. And it sends infinity to a finite point. So it relays the two spheres. It moves around what you call 0 and infinity, but that's fine. So if you're on the plane, you would worry, right? Because infinity is not part of the plane. But for the sphere, it works. So this is a map from a sphere to a sphere. It's really not that far from rotations, actually. It's just a complexified rotation. So here I have, well, naively I have 4 complex parameters, but I can always rescale numerator and denominator and say that AD minus BC is 1. So this is a group called SL2C, this group of transformations. It's convenient to organize A, B, and C, and D into a matrix of determinant 1. if you were to take this matrix to be unitary, then you would get the group SU2, which is actually rotations of the sphere. So inside here, there are rotations. But rotations are a real group. We're working with complex manifolds, so it's pretty clear that we had to complexify it. We could complexify it. So these are complexified rotations. For example, they include transformations as z goes to lambda z. Z equal to lambda z prime. So if you go back to the complex plane, right? If lambda was a phase, this would be a rotation. But if lambda is a generic number, this now includes also rescaling. So that the simplest constant Wild transformation. So these are the transformations which leave the sphere metric to be conformally flat. So they are global conformal transformations of the sphere. This should be opposed to more general transformations of this sort. These are still leaving your metric locally conformally flat. But if you take a generic function here, it's just not mapping the sphere to the sphere in a one-to-one way. A generic function might map a point to two. So this function is special because it maps distinct points of the sphere to distinct points of the sphere. It's invertible. It's defined globally on the sphere. Most complex maps are not invertible. They are not defined globally. So in general, holomorphic functions are very restricted if you require them to have no poles and to behave well. Right? Suppose I was looking for a map from the sphere for an invertible map from the sphere to the plane, for example. But that shouldn't exist, right? Because the plane has an infinity and the sphere does not. That was essentially, let me find the function from the sphere to the plane, so a function on the sphere, which is holomorphic and has no poles, like, which is finite and holomorphic. And there are no such functions. So anyway, I invite you to check, first infinitesimally, that if I look at vector fields on the sphere that are globally well defined and are holomorphic, you'll only find the infinitesimal version of these, which are the z the z, and z squared the z. And of course, there are complex conjugates, the z bar. And then perhaps even try to convince yourself that these are the only global transformations on the sphere to the sphere.
Are we overcounting? Shouldn't we PSL to C instead of?
Sorry, you're right. Yes. Yeah, he's saying that I should not have said, saying determinant 1 was perhaps not enough in the sense I can multiply everything by -1, top and bottom, and the transformation remains the same. That's true. Anyway, so if you're working with spinors, then I would need to be more precise. Now, if I'm given this map moves around the points, right? But it doesn't move them in a completely free way. It allows you to adjust the position of 3 points because you have 3 degrees of freedom. So if I were looking at a sphere with 3 points, Z1, Z2, Z3, I could always find a map like that which sends them to 0, 1, and infinity. It's actually easy to write the map. I just write Z prime equal to z minus z1 over z minus z3 times z2 minus z3 over z2 minus z1. It's easy to see that this map sends z1 to 0, z2 to infinity, z3 to infinity, and z2 to 1. On the other hand, if I had 4 points, z1, z2, z3, and z4, the best I can do is to send the first 3 to 0, 1, and infinity. But the fourth one will go in some different place. Let me call it z, which is called the cross ratio of the number. So z4 minus z1 over z4 minus z3 times z2 minus z3 over z2 minus z1. Particularly, this cross ratio is invariant under transformations like those. So if you have a sphere with 3 points, it has no moduli. I can really always map it to this particular sphere with these particular points, and no freedom is left. If I have a sphere with 4 points, I'm left with one modulus, the position of this fourth point, away from 0, 1, infinity. So I learned that the moduli space of a sphere with 3 punctures is 1 point. And the moduli space of a sphere with 4 punctures is a sphere minus 3 points. Remember, I drew a picture like this for the moduli space of 4. Sorry, you cannot see this. So in one of the first lectures, I wrote a picture like this to describe this moduli space. So this is a sphere with 4 points. You can verify that if you look at surfaces like these with a very long intermediate tube, the ones that are supposed to sort of behave like quantum field theory contributions, these maps to spheres where two of the points, where, say, this one of the points is very close to 1 or 0 or infinity. So the sort of the S and T and U channel pictures I was drawing correspond to regions where this extra point is very close to 0, 1, or infinity. Okay. So now we know how to describe the moduli space of surfaces with the topology of a sphere and any number of external legs. So we need how to describe the moduli space of compact structures relevant for 3-level scattering amplitudes. Any more questions? Now let me ask you a question. How much did you do about the state operator map in conformal field theory? First, did you encounter it? For which quantum field theories did you encounter it?
CFT. CFT.
But which one? Which CFTs? Just abstract CFTs, or did you actually see it happen for a specific CFT?
Just abstract, I think.
Just abstract? Okay. Let me see which board. Okay. So I wonder what's the simplest place to start. Well, first, well, the easiest thing to do is to start from the vacuum. So I could ask, what sort of local operator should I insert to mimic the insertion of a vacuum state? Now, let's look, for example, at this operator. When this operator acts on the vacuum is annihilated by all the positive modes and by the zero mode. So this object behaves like e to the minus s, a minus 1 vacuum, plus e to the minus 2s, a minus 2 acting on the vacuum, etc., etc. Right? Now, suppose I do this transformation from the cylinder to the plane. So we know that the Sx behaves like the Zx times the derivative of 0 with respect of s, which means there is an e to the s. Perhaps let me just move it. Sorry, I want to be careful. I might be making a silly mistake. I don't remember the definition I had given of s. I'm trying to remember if I should put an e to the s or e to the minus s. If I want to map the past to the origin. I don't quite remember if s had tau or minus tau inside in the definition I gave last week. But I'm pretty confident that I need e to the minus s. Because these modes, by definitions, are modes that are supposed to decrease exponentially fast towards the past. And I'm trying to map the past to the origin. So this should be small at the origin. So it must be true that e to the minus s equal to z. So here I should put e to the s dsx equal to the zx, right? So this tells me that the zx, if I map my cylinder to the plane, then the zx, as it approaches the origin, should behave like something finite. Right? Because I'm multiplying e to the s times e to the minus s. Right? So if I want correlation functions on the cylinder with the vacuum in the past to ever match correlation functions on a plane or a sphere, it must be that whatever I put at the origin to mimic the vacuum must have the property that when I bring the zx to it, it does not diverge. Now, you can easily convince yourself that essentially every operator you can write in the free boson theory will cause a divergence in the legs because of weak contractions. The only thing that does not is the identity operator. So if I don't put anything here, then I have a chance to mimic this correlation function. Okay? So, and you can check that this is indeed true. So the first entry of the state operator map dictionary is that the vacuum state maps to the identity operator. Okay? And I'm sure you saw this entry even when you're talking about the generic CFT, because every CFT is going to have the identity operator. Now, I also learned something else, though, because this, when I send e to the s dsx to the far past, I get a very specific state. I get a minus 1 acting on the vacuum. On the other hand, when I map this guy to the origin, and there is nothing to start with at the origin, I'm just gonna get the Zx at the origin. Right? So if you believe that there is a state operator map that relates correlation functions, then it must be the case that this state maps to this operator. Let me just. And similarly, a minus 1 bar acting on the vacuum maps to the Z bar x.
So what's the position dependence of the operator on the right-hand side then?
Well, if I send infinity to the point 0, the operator will be placed at 0. If I send infinity to the point z1, if I send the past to the point z1, the operator will be placed at z1. So the state operator map relates a state in the far past to an operator at the location where this far past has been mapped.
Okay, but it depends. So the state operator correspondence depends on the map. The map
Yes.
that we were talking about.
That's correct.
Okay.
But the map is, the correspondence is going to be the same, not independent of the point. It's just that you need to use the operators at that point. So, right. So to each point in my manifold, quantum field theory has a space of local operators at that point. That is the space which has been identified, the Hilbert space of the theory in a circle. And you can continue. For example, a minus 2 acting on the vacuum. You can easily convince yourself that just by using this expression, that it's going to map to the squared x. Or a minus 1 squared acting on the vacuum maps to the normal, well, a regularized, up to regularization to something like del x, up to some regularization to get rid of the divergence in this polynomial expression. So this way, so on the right-hand side, we're getting pretty much every possible polynomial in the derivatives of x. On the left-hand side, we're getting all the Fock space built out of the zero momentum ground state. So until now, everything is quite nice, but we are clearly missing something. Where are the momentum modes? Which kind of operator could possibly match the momentum modes? Notice that when the x approaches a momentum mode, a momentum ground state in the past, you get an extra contribution from A0 which is just P. Which means that now whatever is the operator which is dual to the momentum must have the property that when the Zx approaches it, it has a divergence. And then the coefficient of the divergence is proportional to the operator itself. No polynomial in your fields is ever going to have this property. Because when in order to get the divergence, I need to do weight contraction, and the weight contraction is going to remove one of the fields.
Where does the divergence come from?
Well, I need to have it because this is 1 over z. So the point is that when I map the Zx back to the cylinder, to e to the s dsx, this object has a divergence in the diverges exponentially in the past when acting on the momentum state. So I need to place an operator at the origin which mimics this same divergence. Now, it turns out that if you allow yourself to move away from polynomials of elementary fields, you can write down such an operator. It's not that difficult. You write down e to the I px. You can convince yourself when dzx approaches this, there is one-way contraction which sort of pulls down an x and gives the divergence. But if you don't feel comfortable with OPEs, you just notice that, you just remember the expansion of x into modes. Let me just put little hats to distinguish operators and numbers. If you remember, the expansion of x involves something like this. Well, I don't remember the factors of 2, but or something like that, right? Now, which means that, at least naively, this operator contains e to the I p x hat. Which kind of makes sense, right? It's an operator of momentum p for the zero mode of the scalar field, which is a reasonable candidate for representing a state of momentum p for the zero mode of x. Right, this operator shifts the momentum of things by p. Right? It's just very elementary quantum mechanics 101. If I want to have an operator which shifts the momentum, I just exponentiate the position. Right? E to the I p x hat p hat e to the minus I p x hat is p hat plus p. So now, of course, we will have to figure out how to actually define this object, right? Because we're already having to be very careful with defining polynomials in the operators by, point splitting regularization or whatnot. Defining an exponential operator is going to be even harder. But these sort of operators you essentially encounter only in 2 dimensions. Because in dimension higher than 2, the fields are typically dimensionful. So it doesn't really make sense to exponentiate a dimensionful quantity unless you want to introduce a scale. But in 2 dimensions, the fields are dimensionless. The scalar fields are dimensionless, so taking functions of the fields, it's a bit more sensible. Anyway, if you want to actually regularize carefully this definition, you can do something like that. You can smear the pointer, smear a little bit the operator. Where this function is 0 far away from the origin, but is still smooth near the origin. Then when you send this function to a delta function, you'll go back to the operator you're trying to define. Now, when you insert a function like this inside correlation functions, you are going to get contributions from weak contractions of x of it and itself. You can, using a little bit of combinatorics or reasoning inside, putting this inside the path integral, you can convince yourself that this guy putting correlation functions will behave as e to the p squared over 2 integral of f of z f of z prime times the divergence that appears in the OP of, in the weak contraction of 2x's, which is log divergence. So in order to make this finite in correlation function, you can correct it by precisely this counter term. So you insert this, the idea is to insert this thing in a correlation function. You do the calculation, and afterwards you take the limit as the function goes to a delta function. And that's your definition of the vertex operator. It's a little cumbersome, but it works. And it already shows you some very interesting properties of this operator. For example, suppose that I compare the definition given in this coordinate system with the definition given in a different coordinate system. Nothing bad happens here. I just change coordinates in this integral. But here I had an explicit function of z. If I was to just try to define the operator directly in the new coordinate system, I would put a log of, z prime, let me call this z tilde. Log of z tilde minus z tilde prime squared. So the 2 definitions will differ. Will differ by something like the integral of f times log of the ratio between this and this. So you can compute that. It's actually finite in the limit where the f goes to delta function. And it tells you that as you change coordinates, the local operator defined at z is not equal to the local operator defined in the new coordinates, but instead there is a very interesting power of the Jacobian. So until now, we only encountered operators which transform with integral powers of the Jacobian. Right? For example, we know that the x obviously transform with a power of 1 of the holomorphic Jacobian. Right? Del bar x transforms with the power of 1 of the anti-holomorphic Jacobian. But this field transforms the fractional power of both. Now, if you remember from your conformal field theory course, there is a relation between in the state operator map, there is a precise relation between the eigenvalue of L0 and L0 bar and the scaling dimension, the power of the Jacobian, which appears in the transformation of the operator. So here, for example, this guy has eigenvalue 0 for L0 and L0 bar, and the identity has no powers of the Jacobian. That's fine.
Can you write the power a little bigger?
So here I have delta equal to delta bar equal to 0. Here, sorry, it's p squared. Right, it's the same p squared that appear here. So here it was L0 and L0 bar were both 0. A minus 1 acting in the vacuum shifts L0 by 1, right? And indeed here I have delta equal to 1, delta bar equal to 0. So I get one power of del z over del z prime and no power of del z bar over del z bar. This guy had L0 eigenvalues which were equal to p squared over 2. And indeed here I'm getting a power of p squared over 2 of the holomorphic Jacobian and a power of p squared over 2 of the anti-holomorphic Jacobian. So this identification that the momentum mode maps to this vertex operator passes the very basic tests. And it happens to be correct. So this is the very first entry of the dictionary about states with generic momentum. And then you can build more entries like A minus 1 acting on P maps to del X Vp, regularized again carefully, and so on and so forth. So this dictionary is half of what we need to make sense of that. The other half is the dictionary for the ghosts. So we're running out of time, so I will describe the dictionary for the ghosts tomorrow. But the main entry, we'll actually only need one entry for the dictionary. So perhaps I will not, because I only need one entry. So describing the whole dictionary for the ghosts is not really needed. So let me give you that entry. That entry is that the ground state G maps to C1, C1 bar. So you might, if you look at the definitions we gave yesterday, you can check that the eigenvalues of L0 and L0 bar acting on this state were actually 1. Even if it was the ground state. And so this guy actually does not map to the identity, even if it's the ground state, but it maps to a non-trivial operator. Now, if your CFT is unitary, it's always the case that the lowest energy state is the same as the identity operator. If the theory is not unitary, that is not the case. Not necessarily the case. In the case of the ghosts, if you want to find something that behaves like the identity operator, you need to look at something like B minus 1, B minus 1 bar acting on the ground state. This is sometimes denoted as 0, just by definition. So it's a convenient, it's an interesting state, in our scattering amplitudes, this is the only state we care about. So this is the only operator we care about. Only operator insertion we care about. If you want to understand better this relation, you might also ask yourself questions about the difference between diffeomorphisms which are natural on the cylinder and diffeomorphisms which are natural on the sphere or on the plane. For example, if you just take translations of the plane, translations of the plane move the origin, so they must be doing something pretty dramatic on the cylinder. So translations on the plane become vector fields on the cylinder which blow up in the past. So in a sense, if you were to put the identity operator on your sphere, the ghosts on the sphere would not remember that the diffeomorphisms are different on the sphere and on the cylinder. This insertion sort of helps the ghost remember that the translations are not a gauge symmetry. Because if you bring another C ghost towards the origin, because the ghosts are fermionic, that C ghost will vanish as it approaches the origin. This corresponds to the fact that vector fields which are good on the cylinder vanish at the origin on the sphere. So that's why we use this ghost insertion. And so we're ready to do calculations, right? This operator here is going to be whatever is the operator corresponding to the matter state coming from that board times CC bar. So to do this calculation, we'll just have to learn how to compute on the sphere correlation functions of those operators over there, correlation functions of the C's, and of the BC's, B's and C's. Because as you remember, we also need that insertion of B contracted with the variation of the metric with respect of the complex structural parameters. Anyway, we'll discuss it more. Very good. Sorry, I'm consistently going over time. I'm not quite sure